All right, here's the review for exam 2. So let's just get this thing started. First question, going back to section 14.1, we've got a function of x and y that's the natural log of 4 minus 4x squared minus y squared. We want to figure out what the domain of this thing is going to look like. And so we'll solve this both algebraically and then also finding a graph of what our domain is going to look like. So in this case, our domain is going to be some projection onto the xy plane, while the range of this function is going to be the z value. So z is going to be the up and down, x and y both are part of our domain. So same rules apply to domains for variables of 2 functions that apply to our regular variables of 1 function. So I cannot divide by 0. I cannot take the square root of a negative number. I cannot take the natural log of a negative number or 0. In this particular case, we have a logarithm. So that's the rule that we're going to use. But our other favorite one is usually the square root. So if you get a square root function, just take the thing that's on the inside, set it greater than or equal to 0. In our case, I'm going to take the inside of the natural log, 4 minus 4x squared minus y squared, and set this strictly greater than 0. Again, because it's a logarithm, I do not want this thing to be equal to 0 either, because that'll end up giving me a thing. I cannot take the log of 0. Log of 0 is undefined, so I need to be strictly greater than 0. But that's where I'm going to get these two pieces from. Move some stuff around, Kansas City shuffle style. And we got x squared, 4x squared plus y squared is less than 0, less than 4. Which this thing is the equation of an ellipse with a y radius of 2 and x radius of 1. So we're going to look for some elliptical shape over here on the right. And since this is a web work problem, I just grabbed those 4 pictures that go with it. And I want to be less than 4, which means I'm looking at the interior of the ellipse rather than the exterior of the ellipse. And since I am strictly less than 4, I don't want to include the boundary, which means I'm looking at option C. The difference between C and B would be that B is including that boundary line there, and C is not. So that's probably what I would take, option C. If it were a square root instead, then I'd want to include the boundary, so I'd pick B. Right. And then we want to find the range of F and talk about its level curves. So if I come back to the function, and maybe just call this thing some parameter, f of t is the natural log of t. Right, where I've got my inside is that 4 minus 4x squared minus y squared. So going back to the standard let's try that one more time. The standard range for a natural log function is all real numbers, right? As long as I'm not transforming this function or restricting it in any way, a logarithm has a range of all real numbers. But our particular log function is being restricted, right? The inside is that 4 minus 4x squared minus y squared. X squared plus y squared together has to be some positive number, which means the maximum value I can plug in for t is 4. So I can get t to be smaller than that. if I'd like. I can get t to be in between. Still got to be bigger than 0, but it is going to have a maximum value up at 4. Since I can't, there are no combinations of x and y I can plug in to be larger than that. So this particular maximum happens at the origin. If both x and y are 0, then t, that inside, is going to be equal to 4. Anything further away from the origin is going to be smaller than 4. So since my input has a maximum value of 4, my range is going to have a maximum value of not 4. What is the right idea? Good work, brain. A maximum value of the natural log of 4. Again, that's our max value for t. So I'm going to just write that in up here for the range, -infinity to natural log of 4, and put a bracket on it. And this time I do want to include 4 because t is allowed to be equal to 4. It's the thing that's not allowed to be equal to is 0. But 0 for t is going to correspond with -infinity if we remember our properties of logarithms. Going to the chat, how do I know if the domain is the inside or the outside of the circle? And that all comes down to this inequality part right here. Because it's 4x squared plus y squared is less than 4. That's going to be everything smaller than 4. So it's that inside part right here. If it were greater than 4 instead, greater than 4 would be option A. Greater than 4 would be everything outside of that ellipse. So I'd choose that instead. Okay, up next, we want to look at the level curves of f. And it looks like I'm going to need to give myself some more space before I can talk about the next tangent plane problem. So if I want to talk about the level curves of f, I want some equation that expresses what our function would look like at a fixed z value. So a level curve means, pick some level being z, because we're just looking up and down. And if I just take a slice of the function at that level, so a cross section at some plane that's parallel to the xy plane, what's my function look like? So what I'm going to do is just replace z with k and then set it equal to the rest of the thing. So z is equal to k, or rather z is k, and this is then the natural log of 4 minus 4x squared minus y squared. And I want to put this equation into something recognizable. So I'm going to solve this thing for x and y, which means I've got e to the k is equal to 4 minus 4x squared minus y squared. If I rearrange this thing, it should hopefully look like 4x squared plus y squared equals 4 minus e to the k, which is really, just some constant number. Call it k2. That last step isn't totally necessary, but the idea here is that k, if I'm looking at a level curve, k is just some fixed number. So 4 minus e to the k, or just, again, it is 4 minus e to the k. Either way, it's just a constant number, meaning I'm looking at 4x squared plus y squared equals a constant, which is the equation of an ellipse. As opposed to, my choices were lines, parabolas, circles, ellipses, or hyperbolas, whichever one of those is correct. And I do need to make a bit of a distinction between ellipses and circles. I mean, you probably could say that something was an ellipse, even if it was a circle, and still get a correct answer. So probably on the exam, we'll take away that ambiguity since circles are just fancy ellipses. Oh, and also they're spelled with two L's. Whoops. Good thing I've got the correct spelling right there. So cool. I got the equation of an ellipse, so I'd want to say that this thing is an ellipse. And here's the first time during the review, first of probably many times, that I'm going to expand on a problem just so we can talk about kind of all of the options that can happen here. So looking at each of the options that are in the pull down that happened on this problem, I want to discuss what each of these things would look like. And so if we have a line, it'll probably look like something like y equals x plus k or y equals mx plus k. Parabolas, we'll get y equals x squared plus k. Or we could also have x equals y squared plus k. We won't be distinguishing between up and down or left and right parabolas. Either one would fit the parabola form. Circles would be an ellipse just without coefficients on x squared or y squared. And hyperbolas are going to look something probably like 1 over x plus k or maybe y equals k over x. But either way, we're reducing our equation down to just something that we would recognize from algebra. I don't think there might be one other shape that I'm not thinking about right now, but these seem like the basic ones that we would probably ask about. Lines, parabolas, circles. And again, we won't ask circles, we'll just put ellipses on there. Or hyperbolas. Yeah, let's leave that as it is. Because from here, oh yeah, hyperbolas could be that, or there is a third form for the hyperbolic shape. X squared minus y squared equals k. There we go. I knew I was forgetting something. Cool. So we can also have square terms in our hyperbolic shape and have it come out to be hyperbolic in nature. So if they're square, usually that means we have linear asymptotes in our hyperbolic shape, as opposed to the non-square terms, we have vertical and horizontal asymptotes in our hyperbolic shape. Okay, with that out of the way, let's go take a look at this next function thing. So say, I've got these functions and I wanted to find some level curves for them. What might they look like? So again, the practice here is just setting z equal to k, or heck, I don't even really need to set it equal to k. I could leave it as z, just get some equation that's like y equals something in terms of x and know that z is a constant. But I want to do some fancy math on all of this. So k equals x plus 1 over 3x plus y. Figure out what these level curves look like. Multiplying this thing over, I'll get, let's try it one more time. Come on. K times 3x plus y equals x plus 1. And through the magic of simplification, I should hopefully get then that y is equal to 1 minus 3k. Ooh, hey, come back. 1 minus 3k times x plus 1 divided by k. Which this thing is a line. Right, it's just mx plus b. If I simplify the thing, multiply the k all the way through, I'll get 3kx, subtract that to the other side. Then I'll have ky, which I'll divide the k over. But it's again just y equals mx plus b. M is kind of fancy in this case, the 1 minus 3k over k. But that's still just a constant number, so I can treat it as a slope. Plus 1 over k, that's also just a constant. And so I get that it's a line. A lot of these actually simplify nicely to become lines. I think this other one's going to do the same thing. So I don't need to worry about the fact that x and y look complicated at the beginning. It's just about what I can solve it to later. So here I've got x squared plus y squared, or x plus y squared is equal to k, which means that x plus y is equal to the square root of k. Maybe I get a plus or minus on here. Probably I do, actually. So then this means that y is going to be equal to, actually, no. Can that be the case? Yeah, because x at y itself could be negative. So y is equal to negative x plus or minus the square root of k. But again, that plus or minus isn't super important here. What is important is that I come back around to the equation y equals mx plus or minus b. So this thing is a line again, even though it starts off looking complicated, right? The function f itself isn't going to look like a line, but its level curves will look like lines. So again, if I just take any cross section that runs through, that's just parallel to the xy plane, I should be looking at a shape that has a couple lines on there. All right, up next, we'll look at, I think I just wanted to look at 3 of these things. I've got k equals e to the negative x minus y. Man, do these all work out to be lines? Apparently that's what I was focusing on. I'll take the natural log of each side. So I've got natural log k equals negative x minus y, which means y equals negative x minus the natural log of k, which once again comes out to be a line. Yeah, I was really feeling line examples today, apparently. Thought I was gonna have at least one that was hyperbolic. Oh well. Is that the end? Yeah, it's the end. You know what? Let's just create one more example because I do want to talk about one that comes out to be hyperbolic. If I have f of xy equals xy plus 3. Then that means k equals xy plus 3. So y is equal to 3, or no, let's try that one more time. K minus 3 over x. That thing is hyperbolic. Parabola. Cool. Now I can say that I've covered that. Well, it ran a little bit into the space for problem 4, but I don't think I'll need to work that far to the right on problem 4. All right, so we want to find a linearization for the function provided at the point 3, 0, and then we'll use that linearization to approximate f of 3.3, 0.01. So if we're finding ourselves a linearization for this mess, I'll first draw our attention back to the equation for a linearization. So L of xy is equal to, so maybe do throw some color in here because it's going to get a little bit complicated without it. L of xy is equal to f of, this will be x naught, y naught, plus f partial x at the point x naught, y naught. Or you know what? Let's not fill all that in. Let's just call it f partial x times x minus x naught. We'll simplify this expression a little bit. Plus f partial y times y minus y naught. Where this thing ends up looking like the equation of a plane, if I just kind of think of these two pieces right here, L and F, as if they were Z. So I have a Z and a Z naught term. I'll kind of get brought in together, and I've done something to fix the sum of constants and all that kind of stuff. But point is, if we're looking for this linearization, I'm going to need a partial derivative in both the x and the y directions. So I should get each of those. Let's start by looking at that. F partial x of xy should be whatever I get if I take the square root of that thing, starting by taking the derivative of a square root. I'm going to get 1/1/2 times the square root piece. So x plus e to the 8y times the derivative of the inside. It's 1/2 times 1. Yeah, derivative of x is 1. I'll just put that in purple. I'll do the same thing for the y partial. F partial y of an arbitrary xy value. Again, same thing. 1/2, 1/2. Reduce the power by 1, so negative 1/2, x plus e to the 8y. Right, derivative of the square root is 1/2, 1/2 square root, whatever. But this time I need the derivative of e to the 8y, which is e to the 8y times 8. I should probably also find f partial x at 3, 0. Which just means plugging in some numbers over here. So this will be 1/2 times the square root of 3 plus 1, which will simplify to 1/4. I'll also want f partial y. Ooh, let's try that one more time. At 3, 0, which will be 8 times 1 divided by 2 times the square root of 3 plus 1, which simplifies to 2. At least I'm pretty sure it does. Yeah, it ought to. Oh, and then also one more step that I haven't quite done yet. Oh no, stop that. Get out of here. Okay, the other step is I do just need f of 3, 0 as well. So I'll take all of this, scooch it down just a little bit, because that's really like steps 1 and 2. Actually, for f of 3, 0. And actually, maybe it makes sense to solve this one out over here. I'm looking at the square root of, once again, this thing probably comes out to 3 plus 1 minus 3, which is -1. Square root of 4 is 2, minus 3 is -1. All right, so now I want to put all of that together to get my linearization. So L of xy is going to be -1 plus 1/4 times x minus x naught, or x minus x naught, x minus 3, there we go, plus 2 times y minus 0. That's my linearization in general terms. I also need to get my linearization at 3.3 and 0.01, which will be -1 plus 1/4 times 0.3 plus 2 times 0.01. Just the differences in the x and the y values get plugged in there. And then whatever number I get there would be my answer. There we go. So there's each of those two pieces. I actually did the math out on that, which I got -0.905. All right, let's take a look at one more problem with tangent planes. So say we've got a couple of curves, R1 and R2, that both lie on the surface of S and intersect at some point P. And we want to find a parametric equation of the surface at point P. So the idea on this one, again, is I'm looking for a tangent plane, sort of similar to the linearization that we just did. And the best way to get a tangent plane is to find a normal vector. I'll also put normal vector in red, N for normal vector. And that's going to be R1 prime cross R2 prime. It's going to be the best way to get that normal vector. So I have these two vectors that I know exist, or these two curves that exist on the plane. but I can find their tangent vectors by taking their derivatives. Find the tangent vectors by taking their derivatives. And if I have two tangent vectors at a point, I can use their cross product to come up with a normal vector at that point. If we change the problem slightly, so say I've got a surface S, which is given by a function of U and V, right? So just a slightly different parametric representation of the function. Instead of saying I know two curves that are on the plane, I could say that I have a parametric equation or a parametric function that describes the surface F, that describes the surface S, the function F that describes the surface S. There we go. The process is going to be nearly identical. I still am going to need a normal vector. But this time, instead of, well, again, it'll be a parametric function, which means I probably shouldn't have said f because that makes it look like a scalar function. It is still a vector valued parametric function. There we are. So the surface is described by by a vector valued function, just with parameters in there. I will still look at the cross product of two vectors, but this time I want partials from both of my two parameters. So this particular problem has already separated. It has already separated the two parameters t and s into their own curve equations. But the surface could also be described as a parametric equation of two variables. And if I want the normal vector, I can again just take partial derivatives with respect to those two parameters at the point and find a normal vector that way. But again, cross product of two derivative vectors should get me a normal vector. So that's what we want to do. So let's start by discussing how to find, we already know the point of intersection. It's at -2, -4, 2. But we want to figure out what S and T are at that particular point. And the way that I am going to do it, because I think it's going to be the best way, is by taking a look at these two pieces. I should be able to say that -t at the point of intersection, -t minus 1 is equal to 2. And on the other side, s plus 6 is equal to 2 as well. Right, I can just set, I'm setting the whole line equal to the point -2, -4, 2, and solving for s and solving for t. I just decided I would cherry pick the easiest example in order to pick up those values. So I think I get that t is equal to -3, s is equal to -4. But we should hopefully see that when I take these things and set them equal to the point, I could get -3 or -4 out of any one of the three coordinates. The y coordinate also looks easy enough. There's just a coefficient on t and s. I mean, I'd have to do a bit more multiplication. But either way, I should be able to come up with -3 and -4. I can also plug in -3 and -4 and verify that I get the correct answer in each. Answering a quick question in the chat, would R partial U prime or just R partial U? Right, so notice that in the way that I've expressed both normal vectors as cross product of derivative vectors, I've used two separate notations for derivative. In the top equation, R1 prime cross R2 prime, I'm using the calc 1 notation for derivatives because they're just an equation of a single variable. So I can just say R prime and hey, that's the derivative. Whereas I'm using the partial derivative notation for RU cross RV because R in that case is a function of two variables. So I need to be specific about which variable I'm taking my derivative with respect to. So RU is basically the same as R prime. It's just that I need to specify, hey, I want the derivative with respect to U, not V. And same thing with then R partial V. It's the same thing as R prime. But I'm telling you specifically, I want to take the derivative with respect to V, since partial derivatives aren't quite complete derivatives in the same way they were in Calc 1. All right, moving on. Now that I know what T and S are, I should find myself some derivative vectors. So I'll start by looking at R1 prime of T. And I should hopefully get the vector negative 10T, negative 10T. Nope, not yet, a comma, minus 4. I know how to do math. 3, negative 1 when I do that derivative. Coming in hot on the other side, I'm going to want R2 prime of S. And it should be the vector. So you've got 46 minus, what was I doing last time I did this problem? I do not know. Negative 6, there we go, that's what I was doing. Negative 6S, 2, and 1. Next up, R1 prime of negative 3. Right, so I actually just have to plug some stuff in. This will get me negative 30. Ugh. Nope, negative 34. 3, negative 1. Double check that against my old notes. Hang on. Well, this is what I get for sleeping right until the moment I started the exam review. Last I checked, negative 10 times negative 30 is in fact positive 30. Minus 4 is 26. There we go. 3, negative 1. R2 prime of negative 4. It's the next thing I'm into. And I hopefully get 24, 2, 1. Okay, cool. That checks out with math I did previously. All right. So up next, I just want a cross product of these things. And we're pretty much in the home stretch from here. N is the cross product of, we want I, J, K. Across the top line, and then I've got 26, 3, negative 1. I've got 24, 2, 1. I don't want a cross product of this mess. So if I run through this thing real quick, 3 minus negative 2 for that K value. Let's see, I've got negative 24 minus 26. And for my Z value, what have we got here? 26 times 2 is 48. Minus 24 times 3, 72. Upon simplification, I got 5. And then I got negative 50. And then I've got negative 28. Negative 28, though, which means 2 comes before 8, if you're writing it out. Hard math, I know. But cool, we've got ourselves a normal vector. So the last thing to do is just put this thing into the equation of a plane, which is 0 equals our point minus our little normal vector times xyz minus the point. So n times x minus x naught. Right, whatever our thing is minus our point. So that should be 5 times x minus negative 2, right? That's what it was. Yep. Cool. Minus 50 times y minus negative 4 minus 28 times z minus 2. That's what I get. Negative 24 somewhere? Which spot do we think? Oh, wait, I think I just found it. Yep, I think, okay. Let's hang on just a second. Yeah, 72 minus 8 is the same thing as 74 minus 50. Yep, there's a mistake in there. Yep, negative 24 for that z coordinate. Nice work in the chat. Yeah, negative 24 on that z coordinate. 48 minus 72 is negative 24. Yeah, well, it's the simple stuff that kills you, I guess. Cool, but that's going to be good enough for the equation of our line, I would think. Leave that as it is. All right, up next, we got a chain rule problem. On here, I'm probably going to look at just doing out one set of these. So I'm going to look at finding the derivative of z with respect to s, where I've broken down, what that chain rule should look like. If I want the derivative of z with respect to s, where x and y are both functions of s, then I'm going to need to look at the derivative of z first with respect to x, and then I'll do the derivative of x with respect to s. So it's like I've got to get all the way down in order to do that. So what does that mean for us? That means I'm going to want some partial derivatives of z with respect to y and to x. We'll fill in that top bar first. If I'm doing a derivative of, I'm looking at, hey, oh boy. It's possible my tablet has just crashed. So we might lose the video feed here in a second. Oh, no, there it goes, it came back. Okay. So we've got that function. I want a derivative with respect to x. And if I do that, the derivative of sine is going to be positive cosine times the derivative of 2x is going to bring a negative 2 out in front. So I've got negative 2 cosine of negative 2x times cosine of 8y. We'll also look at the derivative of z with respect to y. Derivative of cosine is negative sine, and multiply by the derivative of 8y, which is 8. So we'll still have -8 cosine, or -8 sine of -2x times the sine of 8y. Keeping things consistent, I'm highlighting the changes with color. Those are the pieces that change. After that, I need derivatives of both x and y with respect to s. If I do that derivative on x, I'm just going to get 2s. And if I take a derivative of y with respect to s, I should get -2t. Let's not make this overly complicated. There, yeah, -2s versus -2t. If I take derivatives with respect to x and y. So now in the end, I just got to take these couple things and replace x and y in there. So where am I going to have space to write all that down? Actually, probably just off here to the right. So if I'm looking to get a derivative with respect to s, this thing should be, we'll do z partial s is equal to, I've got -2 cosine of -2 times s squared plus t squared. Close both sets of parentheses times cosine of 8y where y, 3 minus 2st, this whole thing multiplied by the derivative of x with respect to s, which is going to be 2s. Good enough. This thing is kind of long, isn't it? Added to that, I need the derivative of y with, or the derivative of z with respect to y, and then s. So this thing becomes -8 sine of -2 times that x thing, s squared plus t squared, times the sine of 8y I've got 3 minus 2st. Multiply that whole thing by the derivative of y with respect to s. All right, hopefully we can zoom out and collect all of that. No, did I make another mistake in that last problem? Shouldn't be 52 instead of 48. Might be. Hold on a second. I've got my notes right here. I can look back up at it. Oh boy, yeah, it is. 2 times 26 is definitely 52. Yep. So yeah, -20k. I'll go back and change that. Right here should have been 52, which does in fact make this thing -20. Again, nice catch down in the chat. Done and done. But if we had maybe, okay, then ZS goes down here. If we had also needed to do this thing for T, which I guess the problem tells it is, we do, but I'm going to skip it for now. This thing should have been 2T and negative 2S. And I can do that whole thing again, just replacing the derivative of S terms with the derivative of T terms. But that'll get long, and we're already going over on what I was hoping to do anyway. So I'll just do part S. All right, up next, what have we got? We're looking at a bit of a concept question, along with a bit of some math. So if we want to find the maximum rate of change, the maximum rate of change of a function should always point in the direction of the gradient, which means if I find the gradient, then the max rate of change should just be the magnitude of the gradient. So let's give that thing a shot. So for starters, I need the gradient of f, which I need first the x partial, then the y partial, and this one's got a bit of a fun derivative, doesn't it? Looks like negative 1 times e to the negative 3xy minus a negative 3y times x e to the negative 3xy. Right, so if I take the derivative of that exponential thing, I'm going to have a negative 3y that comes down. So hence the plus 3y, x times e to the negative 3xy. But that's not the worst step in the world. After that, I want a derivative with respect to y, which means this thing will end up being positive 3x squared times e to the negative 3xy on that y coordinate. Or at least that's what I get when I plug stuff in. Up next, I just have to plug in some numbers to my gradient. I'm at the point 3, 0, so I'll plug each of those in. And what do we get? Fortunately, plugging in 0 for y means that the exponent on each of these three pieces is going to be 0, and e to the 0 is 1. So I'm going to get negative 1 plus 0. And on the other side, 3x squared. So 3 times 3 squared is 27. So if I just clean that up, negative 1, 27. And then also, I'm going to want the magnitude of that vector. So the magnitude of f of 3, 0. This ought to be the square root of negative 1 squared plus 27 squared. And hopefully my math worked out right on this one. 27 squared should be 729. Yeah. Plus 1 is going to be 730. And now this is kind of a fill in the blank question. I've got all the math I need. The maximum rate of change is that value I just calculated, 730. Keep in mind that the max rate of change should be a scalar value. It's just asking for a number. So I don't want a vector in there. But the direction is asking for a vector. And also notice your answer must be a unit vector. But fortunately, we've already done the math to get all of that. I have a vector that goes in the direction that I want, which is negative 127. And I know the magnitude of that vector is root 730. Oh, so I can just plug that in. And oh boy. Up next, we've got the favorite problem in this set. Finding minimum and maximum values. So I wrote out sort of the three steps that we're going to need to take to find minimum and maximum values that are going to show up on our function. And the way to do that is step one, we're going to want to find all of our critical points. Step two, we'll find critical points on the boundary. So the first one is finding just critical points that exist on the function. So that'll be like the interior of our domain. We also need to look at critical points along the boundary because the maximum and minimum on a closed region are either going to occur at critical points or they'll show up somewhere on the boundary, since we could get just cut off as the function is increasing or decreasing. And once we've done those two steps, then we can just plug them all in and see what happens. Our biggest number will be the maximum, our smallest number will be the minimum. But with all that out of the way, let's take a look at what we got. Our domain is going to be the circle, or the interior of the circle, x squared plus y squared equals 36. So that's a circle with a radius of 6, and it's centered at the origin. So I just need to have my critical points be inside of that. So to do step one, I need partial derivatives. I want f partial x, which is going to be just 2x. Nice, easy enough partial derivative. I'm going to need to set that equal to 0 to find a critical point. I'm also going to want f partial y, which is just slightly more exciting, but only barely. I get what? 8y minus 16. I also want this thing to be equal to 0. So I get x equals 0 on the left, and I'm going to get y equals 2 on the right. Cool, so that gives me my first critical point at 0, 2. If this were a more complicated set of partial derivatives, I would need to like substitute a value for x into f partial y, or substitute a value of y into f partial x. But this was a completely separable function, which makes it nice. I just needed to solve each one individually. I get a number right away. So kind of a nice looking partial derivative set. All right, on to part 2. We want to check our critical values on the boundary. And our boundary is the circle x squared plus y squared equals 36. Right, the whole domain is less than or equal to 36, but the boundary of our domain is just x squared plus y squared equals 36. Which I am just going to use a quick replacement trick here. Solve this thing for x squared. So 36 minus y squared. And if we take a look back at that initial function, I already have x squared just kind of chilling in there and no other x values, which means I could replace the entirety of x squared with 36 minus y squared, and then I'll have a function of only y. So along the boundary, my function becomes f of 36 minus y squared, comma y, which is a function that depends only upon y. And it looks like this. 36 minus y squared plus 4y squared minus 16y plus 34. What's that other number hanging out? Number's about to not matter anyway, because I'm just about to do something fancy over here. And let's go ahead and simplify that a bit. Do I want to simplify that? Nah, I'll simplify it in the derivative. It'll be easier that way. If I look at the derivative of y, notice it is just a derivative now because it's a function of only one variable. So I can go back to my f prime notation from Calc 1. This thing becomes negative 2y, negative 2y plus 8y minus 16. And again, I want this thing equal to 0, which means that y is going to be 8 over, well, it'll be 16 over 6, which I'll just call 8 over 3. And then if y is 8 over 3, that means that x squared is 36 minus 8 over 3 squared. If we just kind of follow this thing over to here, which means that x itself is some ugly looking thing. Plus or minus the square root of 36 minus 8/3 squared, which I went and got a decimal approximation for this thing, plus or minus 5.3784. All right, and then just looking at like a quick, cursory glance at this thing, just a sanity check to make sure that my points make sense. X is about 5.3 or about 5.4 maybe, which means that it is less than 6. So this thing looks like it could still be on that circle. Right? If I'd gotten a number that was bigger than 6, that would probably, that would become a problem. But our number is less than 6, so that thing is probably on the circle, so that looks good. So I'll keep charging forward. The next big thing, stop, get out of here, is I want to actually look at the domain of this thing, or sketch out the domain of this function. Not my cleanest ever. You know what? I'm just going to pull out a ruler. Come on. There we go. Okay. There we go. Here's my circle, right? Circle of radius 6. It's going to be centered at the origin. And what was I doing here? Right. I wanted to look at sort of the boundary points that we have. So we just found our points that are at a y value of 8/3, which means they're pretty low. We have that x and y are at plus or minus 5.4 8/3, it's more than 2, but not quite 3. So looking at points like here and here. We also found our critical point at 0, 2, which means something about here-ish. Oh my God, stop. We also have maximums for y. Maximums and minimums for y. Right? Being that since I got a function in terms of y, y has a maximum value of 6 and a minimum value of -6. So my y value has a maximum value of 6, a minimum value of -6, which means I also need to include those boundary points as I'm looking at my boundary, or maybe there's boundary values as I'm looking at my boundary. So right here and right here, which means in addition to all the other points I've put together, I've got 0, 6, and I've got 0, -6. I'm going to need to check those as well. The points I got up here, I forgot to actually write down what they were. But it's going to be 8/3, and then plus or minus 5.3784. So altogether, 5 different points that we're going to need to check. Finally, point 3 was just checking them all. So I want to look at f of 0, 2. I'm going to want to look at f of 8/3 positive 5.3784. I'll also need f of 8. Ooh, wait, hold on a second. These are all backwards, aren't they? The x value is 5 point whatever. Y value is 8/3. There we go. So this is negative 5.3784 comma 8/3. Suppose I should come up here and change that real quick. Just take this and scooch it over. 8/3. There we go. That looks a little better. And oh, hey, look, we've once again run out of space. All right, and then also finally, I want to look at f of 0, 6 and f of 0, -6. Okay, I've got all of these things, and I just gotta plug them in and see what happens. So I did that already, plugging it into that original function. I'm gonna do the math out on this first one. 0 squared plus 4 times 2 squared minus 16 times 2 plus 34. I guess also that 0 should be in blue because I'm plugging it all in. I got negative 18 on this one. Skipping ahead through all of the extra math that I did. both of these things come out to 12.7034. Which we were expecting that they should come out to be the same value, since in the original function I just have x squared. So it was definitely going to come out positive. And then I also needed to check my boundary values, where I got 142 for the top point, and I got 238 for the bottom point. So now all that's left to do is identify the maximum and the minimum, which are the largest numbers and the smallest numbers. And there we have it. Yeah, max value and a min value. So there's also that second derivative test that shows up in this problem. And we're going to look at a problem like that a little bit later on. But first, moving into chapter 16. All right, actually, before I do that, I'm going to answer a question from the chat. So the chat managed to catch that I'd switched X and Y before I did, I think. Oh, no, they were, yeah, right at the beginning. Yeah, there should have been a square root over that 36 minus y squared. Yeah, you're probably right. I should have done that. I ended up plugging it in correctly. I just wrote the function notation down wrong. But yeah, you were right. That should have been that. The other question was, what happened to that -2? When does the -2 in f of x, y become plus 34? Oh, did I write something down wrong? Oh, that is a really good question. When does it become plus 34? Apparently it only becomes plus 34 when you write it down wrong. So I was skipping ahead in my work, it looks like. And I had already simplified 36 minus 2 and got 34. But yeah, you're right. That should have been a -2. So looking at my work instead of the original statement of the problem, just copied something down wrong. Which probably means if you came down here and tried plugging in -34 there, you would not get -18. But let's hope that I plugged in the right number when I was doing the work beforehand. Pretty sure I did. All right, let's take a look at this work problem. So write down the given line integral in terms of t, or rather this one isn't work. I've just written down the equation for work because I think that'll be important. So if we're moving beyond just the algebra definition of work that you have in an algebra approach to physics, and look at the calculus definition of physics, then it's some force field dotted with a position derivative vector, and we integrate that thing. So f dot dr, or rather the integral of f dot dr is work. And I think that'll be important if we look at similar problems to this one. We're often able to say, find the work given a couple of things, and then you'll have to do the rest of just knowing we need f dot dr. But what do we want? We want to integrate y ds, where we know something about the curve. So let's take a look at what ds should be equal to. And ds, we know from, this is section 16.2, ds is the square root of x prime squared plus y prime squared, or x prime squared plus y prime plus z prime squared if we're in 3 dimensions. This thing's only in 2 though, so we only need to look at that. So we're looking at negative 2t squared, or negative 2t squared plus 1 squared dt, which I can just simplify to 4t squared plus 1 dt. Then I had what? Y times ds. I know ds now. I know that y is t. So plugging some stuff in up at the top, this thing looks like t times the square root of 4t squared plus 1. And the dt is already there for us. Cool. Where a and b are going to be 0 and 1. We're getting that from right there. And then we just have to evaluate that integral. So we wanted to evaluate a line integral. The easiest way to do that is to just turn it into a standard Calc 1 integral, so that instead of going over some curved line through space, it can just go across some straight line that's hopefully either our x or our y axis, or I guess the t axis, because we're using a parameterization. So let's plug stuff in and see what happens. If I actually want to integrate this thing, I'm going to want a u sub. So I'll have u be 4t squared plus 1, meaning du is, what is that? 8t dt. Oop, nope, just dt, no dt squared. Let's maybe slide that thing right up there. Just a little bit out of the way. And we'll substitute some stuff in. That means that this integral becomes the square root of u times du So notice that that t that used to be on the outside is going to become part of du. I'll highlight it right there. But we still have that 8 to deal with. So 1/8 times all of this. But that's a thing that we can integrate. This becomes 1/8 times, so u to the 1/2 integrates to u to the 3/2 over 3/2. So times 2/3 u to the 3/2, which we start simplifying some of this stuff. 1/8 times 2/3 is 1/4 times 1/3, 1/4 times 3, that's 1/12, times 4t squared plus 1, evaluating this thing from 0 to 1. Then if we plugged all that in, what do we get? 1/12 times, oh, whoop, to the 3/2. This will be 17 to the 3/2 minus 1 to the 3/2. Let's call it 1. Yeah, hopefully that looks all right. Okay, coming back to answer another quick question from the chat. Why are 0, 6 and -6 critical points in the previous problem? So if we scroll back up to here, and we'll look at this picture of our domain. Oh, so there's that circle with the red lines on top and bottom. How could I even put them in the right spot? I know based on what my domain is, because it's this circle, that y has maximum values of 6 and -6. Where does, oh, wow, I'm off my rocker again, aren't I? Yeah, I have no idea where that that 17 came from. We'll fix it in a second. I must have squared the 4 on accident. But yeah, so back to 6 and -6. Maximum values for y are at 6 and -6 because I cannot go beyond the circle of radius 6 that's centered at the origin. So 6 and -6 are my boundary values for y. I can't go bigger than 6. I can't go less than -6. So it's for that reason that I need to consider 0, 6 and 0, -6 as critical points. But they're less of critical points and more like boundary points. But I still have to check them when I'm searching for my absolute maximum and minimum, because max and mins can show up on the endpoints of the boundary. Yeah, back down to here. Yeah, I don't know what I was doing. If I plug in 1, 4 times 1 squared is 4, not 16, plus 1 is 5. Pretty sure that's where I got 17 from. I'm gonna blame that on lack of sleep. Or not enough sleep. No, not enough sleep is lack of sleep. I'm really doing well today. Hooray for me. Okay, cool. Let's call that good and move on to the next one. All right, another one from line integrals. Got problem 9. So evaluate the line integral with the following properties. We're going to find some r prime or some r of t, plug some stuff in, evaluate some things. Where c is the arc of the circle, x squared plus y squared equals 16, that goes counterclockwise from 4, 0 to 0, 4. So that's way more than I needed it to be, but whatever. So if I just draw my coordinate axes up here real quick, I'm going from 4, 0 to 0, 4. 4, 0 is this point on the x-axis. 0, 4 is that point up there on the y-axis. Let's move these a bit closer together so it actually has a chance of looking like a circle. And I want to go counterclockwise, which means I'm looking at this arc right here. Right, that'd be the direction that we're going if I'm traversing that arc. And also, if my hand was a little steadier, it would actually look like part of a circle, but oh well. So that's the arc I'm looking for. It's just a quarter circle. And I want to parameterize that circle. And that parameterization, I'm probably going to use the trig one. So it's a circle of radius 4. So my parameterization is probably going to be 4 cosine t for x. And 4 sine t for y. Wait, what am I, no, slow down. Slow down. That's not a parameterization. That's just the circle. Yeah, 4 cosine t for x, 4 sine t for y. I don't know why I was trying to square them and add them up. because my notes are just something crazy. Yeah. So yeah, that curve can be parameterized by 4 cosine t for x, 4 sine t for y, just like we said. And then our angle, our t value, is going to go from 0 to pi over 2. Because 0 is going to be my starting angle, right? If I just go to the unit circle, the x-axis is an angle of 0 up to the top, which is an angle of pi over 2. So t goes between 0 and pi over 2. Again, the unit circle is going to help us out with that one. Up next, what else are we after here? Another variation I'm seeing on this problem is going from 4, 0 to 0, -4, which would be straight down on the unit circle. So straight down the y-axis, and that's an angle of 3 pi over 2, if that one comes up. But probably just knowing 0 to pi over 2 should be enough. Or if we go all the way over to the other side of the x-axis, so straight left, that's an angle of pi. But yeah, knowing those axes in their angle forms is probably going to be helpful. But up next, some of the things we're going to need, we'll need dx. Which now that we know that x is 4 cosine t, dx is -4 sine t. And we'll want dy as well. Which should come out to 4 cosine t if I take its derivative. So getting this part here in the box, I just need to throw some pieces in here. I'll have 6 times 4 cosine squared. Or cosine t squared times dx, which is -4 sine t, plus 2 times y, which we said was 4 sine t, all of that mess squared, times, what do we get? 4 cosine t. All of that times dt. That's all that's going to go in the box. So notice the big difference between this problem and the last problem is on the previous one, we were integrating y ds, which means that we need some kind of a dot product, probably some kind of a dot product between some vector function and some vector derivative function. But this problem has already separated those steps out for us. So it's already separated it into a dx term and a dy term. So we don't need to go through the process of solving for ds. Presumably that process has already been taken care of for us in this separation. So all we needed this time was dx and dy instead of having to solve for that ds thing from last time. So I just needed dx and dy, plugged those in, multiplied some stuff together. This thing integrates from 0 to pi over 2 still. That hasn't changed. And then we actually have to integrate this thing, which ends up being not so bad. I'll just kind of rewrite that thing here. The integral of, hey, slow down. The integral of that, I'm just going to use, no. Dang it. Come on. Do the thing I'm clicking. Cool, I want to integrate this thing. from 0 to pi over 2. Doing so is going to get me to 6 over 3 times 4 cosine t cubed plus 2 over 3 times 4 sine t cubed, evaluated from 0 to pi over 2. So if you'll notice, we already had this thing set up perfectly for a u substitution, so I wouldn't want to distribute anything. Right, I'll start by saying u is 4 cosine t, which means du, negative 4 sine t, dt. Do the same thing for the y term. I guess we'll call it v equals 4 sine t, so dv is 4 cosine t. Makes it really easy to just say, okay, x squared is x cubed over 3, y squared is y cubed over 3. Just plug some stuff in. Then we get the super fun task of plugging in 0 and pi over 2. So if I plug in pi over 2, this will be 6/3 times 4 cubed plus 2/3 times 0 cubed minus 6/3 times, ooh, wait, nope, I have these backwards, don't I? Cosine of pi over 2 is 0. Sine of pi over 2 is, sine of pi over 2 is 1. So there we go, 1 times 4. Then plugging in the 0 part, now this is 4 cubed plus 2/3 times sine, which is 0 cubed. And then what do we get when we slap all that together? I got 4/3 times 64. Or, nope, sorry, negative 4/3 times 64. So negative 256 over 3. All right, and is that the end of the problem? Nope, I have one more. Oh, right, conservative vector fields is the last step. Okay, so conservative vector fields are way easier than I think they look. So the idea behind a conservative vector field is that if I have one, I just want to integrate each of x, y, and z and see what I get. And then I'll compare the results and see if I actually have a function that could work. So if I integrate the x piece, we'll look at x, we'll look at y, we'll look at z. So I'm going to integrate negative 2y, negative 2yz e to the x z dx. I get negative 2y e to the x z plus c. If I do that same thing, integrate, but this time it's integrating negative 2 e to the x c dy, I'll get negative 2y e to the x z plus c. If I integrate negative 2xy e to the x z dz, I get negative 2y e to the x z plus c. So I haven't picked the most exciting example because in each of these cases, all three parts integrated to the same function, which means that there's no real combining that I have to do. I just look at each piece. I want to pick out all of the unique terms that show up in these integration pieces, and then just add them all up to say that that must be what my function is. These things all came out to the same thing, which means my original function f should be just 2y e to the x z. So that's all I got. Right, not too bad. But if there were some other term that showed up in here, and maybe we'll just look at another example in a minute, so I don't want to talk too much about it here. But if there were other terms, say if there were a term in that x integral that only depended on x, I could add that in. If there were another term like in the y that only depended on y, I could add that in. But again, I'm just looking to only include each unique term in each of these integration pieces. But cool, negative 2y times e to the xc. Technically, we were probably supposed to check to see if this thing was conservative, but I think this is a good enough check. It'd be somewhat easy to find a contradiction in this step where we integrate each piece to end up finding out that, okay, yeah, clearly this thing can't be conservative because of whatever piece. But let's use the fact that we have a conservative vector field to make life easier on us. So the concept at play here is that if I am integrating through a conservative vector field, the path that I choose to integrate along does not matter. Any path I take to a conservative vector field, if I'm doing an integration, will end up just being the result of my function evaluated at the final point minus my function evaluated at the initial point. So it should look exactly like the fundamental theorem of calculus from back in Calc 1, which just says that, the integral from a to b is f of b minus f of a, which means we just want to know what b and a are. So if I set up something for a, that's going to be r of 0. Maybe I'll color that in green because we're looking from 0 to 1. So a will be r of 0, and it is the point 2, negative 5, 0. If we just plug that into the curve that's provided, then that means that b should be r of 1. And if I plug in 1 for t, I got 3, negative 4, 0. Which means that my integral should just shake out to f of 2, negative 5. Oops, let's try that one more time. 3, negative 4, 0 minus f of 2, negative 5, 0. Right? This is f of b minus f of a is how we want to be thinking about this. F of b minus f of a. And what's it work out to? Negative 2 times if y is it's negative 4 times e to the 0, which is just 1. So negative 2 times negative 4 minus negative 2 times, if I plug in that point, again, the exponent on e is 0, so this is just negative 5. Comes out to 2. Did I do that right at all? No, I didn't. -2. Wow. Man, glad I'm not taking the test right now. Jeez, it would not go well. All right, cool. So all told, this -2 that we got right here means that this answer box is -2. Okay, I hope that that's the end of the problems that I left for myself to do live. Oh, good, it is. All right, a couple more that I've already worked out a bunch of the math on, and now I just want to talk about them. So here's the triangle problem that's shown that I know we had a lot of questions about it on the max and min homework set. In the homework set that we did, we only had to parameterize the top line. So the line that went from 0, 7 to 8, 0. So from this point to this point is all that we were parameterizing when we did the work. But we need to actually solve for critical points that are all the way around the boundary. So we end up with these 3 different boundary lines that are represented by 3 different equations. One with a positive slope, one with a negative slope, one with a vertical slope. And we'll find critical points on each of them, which you end up finding one critical point that is on each of the sloped lines. I think there's also a critical point that shows up on the vertical line. Pretty sure 0, 0 works out. I don't remember exactly what it ended up not being important. There's another one like right here in the middle. It was at like 0, 2, I think, or 2, 0 rather. But yeah, whatever, getting ahead of myself in ways that I didn't really care to. So on this particular problem, when we're checking for the maximums and minimums, we just have to look at all 6 or maybe 7 points that we end up finding. So we end up finding one true critical point. We find either 2 or 3 critical points that are on the boundary. Yeah, there is in fact a critical point right here. So there are 7 altogether. Put that one in green then. So there are 3 critical points in the boundary because there's 1 on each line. And then there are also 3 endpoints that I have to check as well. So checking the intersection of each of the 3 boundary lines. So check all 7 points, and then the largest is the maximum, the smallest is the minimum. Here was another fun one. Oh yeah, I wanted to talk more about conservative vector fields. So this whole mess that we've got here, when we're checking to see if a function of 3 variables or a vector valued function of 3 variables could be a conservative vector field, we have to see, could this vector field have come from some initial function? And it ends up saying, okay, it only works out if like these 3 different equations are all true. And I think another way that we write it down is like, we look at the difference between each of these things has to be 0. It ends up being like just an awkwardly worded, awkwardly complicated question. So I want to shed a little bit of light on this here. It's going to make more sense, I think, when we do more chapters or more sections in chapter 16, but we're pushing that off until after exam 3. So let's see if we can just kind of get a decent enough look at it right now. So if we're looking at the first one, when we say p partial y needs to be equal to q partial x, it helps to remember that p, q, and r, which are all the components of my vector field that I want to check to see if it's conservative, each of p, q, and r are supposed to already represent a partial derivative. P is meant to already represent f partial x, little f partial x. Q is meant to already represent little f partial y. R now being the third one is supposed to already represent little f partial z. And I think if you think about it from that perspective, so try and take a step back and think about what P, Q, and R mean in terms of little f, this ugly looking set of three equations that just has way too many letters in it, I think starts to look a little bit nicer. So all it's trying to say is that anytime I take the same two sets of partial derivatives, I need to end up with the same answer. So if I look at P partial Y and Q partial X, in both of those, I have theoretically taken a derivative with respect to both X and Y. P already has partial X on it. I'm just adding partial Y in. Q should already have partial Y on it. So I'm just doing a partial X, which is where I realize I'm pointing at my screen and that doesn't really work for you. Let me actually start marking stuff. Hey, stop. I said pick that thing, you dingo. Okay, so that this first equation here, P partial Y equals Q partial X, this is really just trying to say that fxy is equal to fyx, right? So that I'm taking partial derivatives both with respect to both x and y. If I look at the next one in, I'm comparing both x and z partial derivative terms. Looking at the third equation, I want to compare both y and z partial derivative terms. So to see if this thing ends up being a conservative vector field, I just want to look at those sets of partial derivatives. So I get, I just created a table here where I'm looking at all of my partial derivative terms. And I see that if I compare, come on, man, if I compare these two guys, which are both terms that have derivatives of x and y in them, I get 2 in both cases, which means that that first set looks good. But then I also have to compare x partials with x and z partials together in both orders. And I get, if I look at those two sets, I should get the same thing if it's a conservative vector field, but I don't here. Right, I get 0 if I look at one case, and I get yz if I look at the other case. So that step fails. I can also look at the y and z partials, but once again, I find that those don't work out either. In one case, I get 0, in the other case, I get xz. So not so good there. Meaning in the end, when I'm asked to say, check all of the requirements of the extended component tests that fail, making the line integral path dependent. I would say that the xz partials failed and the yz partials failed, which is why I have boxes B and C marked over here. So that's the textbook explanation of how you're supposed to do this thing, which even at my best explanation, I think it still comes out more complicated than it's worth. So instead, I want to look at just integrating the x, y, and z components individually and see what I get. And I think you can see if we look at integrating these three things, they don't all match up. If I had a conservative vector field, I would need to get the same thing, or at least things that could potentially mesh together to make the same initial function. And there's no way to make these three things agree with each other. The x and the y parts are already cool, which is why the x and y partials were fine. But anytime I try to compare it to the z term, I get it that this thing falls apart, that x, y, z squared over 2. That's not going to fly. So because that z component doesn't mesh with the other two, I must not be looking at a conservative vector field. Yeah. Oh, and I did leave myself one last problem to actually do out, but this one should go all right. So I said I wanted to also look at that second derivative test. Hint, hint, wink, wink. to, maybe make sure that we understand what this concept is over here. So this time we're not even given a function. We're just told what the second derivative terms look like at a critical point. So we know that 1, 2 is a critical point, and then we want to evaluate this capital D term at the point. So that second derivative test, see what comes up. So if we look at that second derivative test, the thing that we really care about over here is the sign of D. Right, I want to look at whether or not whether D is positive or negative. If D is 0, it doesn't tell us anything. But if Z comes out positive, then we're in business. So that's the first step. It's just checking to see if this thing is positive. If D is negative, then we know we have a saddle point. But if D is positive, we're going to have some more things that we want to look at. So D should be 2 times 10 minus 3 squared. Right, so the double x partial times the double y partial minus the mixed partial squared. Doing so, that's 20 minus 9, so 11. Making this thing greater than 0, which means I want to start investigating what kind of a point I have. So if I want to decide if this thing is a maximum or a minimum, all the textbook problems and the web work problems all say you have to check specifically the second x partial derivative term in order to decide what this thing looks like. And I want to expand on that just a little to say that it doesn't actually matter which second derivative term we look at. I can either look at the x double partial or the y double partial in order to figure out if I have a maximum or a minimum. Because the only way that D can be positive is if both second order partial derivatives have the same sign. Bingo. Well, Rufus got scared about something. Okay, so like I was saying, the only way that D comes out to a positive number is if both second order partials have the same sign. If they have opposite signs, then I'm going to have some negative term minus a square term, which can only ever come out negative. So I just have to look at either one of my two second order partial derivatives. So either fxx or fyy. Because those two are going to have to agree with each other if I'm going to have a maximum or a minimum. If both terms are positive, that means it doesn't matter which direction I look from. Both of these things are going to be concave up. And if both second order partials are concave up, I must have a minimum because all the concavity is pointing up. If both terms are negative, that means that this thing is concave down, because remember, second derivative tells concavity. So if both terms are negative, both directions look concave down, meaning I end up with a maximum instead of a local minimum. And then finally, a saddle point happens if one direction says concave up, but the other direction says concave down. That means I must, hit a saddle right in the middle of it. So looking at our thing, I've got both second order partials are positive, which means that this thing is a minimum. Actually, maybe let's highlight all this stuff in the other color. All these things are a minimum. So over here, minimum.